Okay. So last session we finished the deadlock problem, the detection algorithm, and recovery, banker's algorithm. These are the things that we covered last session. So then I asked you to continue with the PA1 implementation, and today you have to basically keep asking questions. We're going to go over some exercise questions. The solutions to those are already in the lecture notes, so don't worry about it. If we don't cover all of them, that's fine. But we want to cover the ones that are kind of at least questions amongst many of you. So feel free to say, yeah, we know this, or no, let's talk about this one a little bit more. Okay. So first the logistics, and just to quickly go over the topics that we have learned so far in the semester. And again, pause me and stop me and let me know, if that topic was not clear or something. And then either tell you that, okay, this is not as important, or what is important in that. So right here on Tuesday next week, and make sure you're on time. We want to probably start the exam as soon as possible. We have some logistics, handing the papers, and then when at the end of the exam you have to hand it back. We have to check your IDs, and these also take time. We don't want to make a mess. This room is not very big, so let's have it organized together as soon as possible. So the topics for the midterm are basically chapters 1 through 7 from the book, and let's go over them one by one and see. So in chapter 1 and 2, overall, we learned about the operating system, like an overview of what is an operating system, and what are the design goals of an operating system from the different perspective, the user, system design, and what are the responsibilities, what are the major components, processes and threads, scheduling, I/O management, memory management, and what was the design approaches for the operating system. So they were, microkernels, layered approaches, monolithic, and so what was the pros and cons of each of them? Why cannot we implement microkernels, for every operating system? What was the issue that grew and ended up again, there's not very specific questions that. What was wrong with MS-DOS? No, it's not like that, but you have to know what was the issues. Okay, I'm going to tell you in a minute. Chris also asked this last session. So I have not finalized your midterm yet. The reason is I'm trying to make it multiple choice because the grading is a little bit easier and I can give you your grades faster. And but on the other hand, there are issues with the OS type questions that are really difficult to put into multiple choices, and questions that basically you can read and answer in 1 or 2 minutes. And then some of the questions are, for example, like Gantt charts. You have to spend like a few minutes and then you get to produce answers. But in multiple choices you don't have partial scores, partial grading. So these are the issues with the multiple choices. So by default, the questions are essay type questions, 7, 8, 9 questions roughly. Each might take several minutes. And but again, I'm trying to either put the whole thing in multiple choice, or it's going to make it a lot of hassle if I want to make half multiple choice, half essay. But again, if that's what's going to happen, I'm going to see. So did that answer you at least somewhat? The short answer is it's not finalized. But yes, then we went to processes. When we learned what are how a process is represented in the operating system, what is the PCB, process control block, how the processes create and get terminated. We learned how fork and exec work. And again, you have to make sure that you understand all of these completely. You could solve the problems that were in those topics and lecture notes. At any point, if you wanted to, not for so long, but we can quickly go over the other lecture and then, just see what's going on if you miss something. And then we learned what is a context switch, and then what happens during context switch, what is, the process states going from, creation and then ready and then blocked or waiting and then terminating, running, and all those. And then process queues, that each process was either they were running, on the ready queue, or they were waiting for something, was an I/O, or they were waiting in the ready queue, or they were waiting for later on we realized actually like a semaphore or something, or any other resource. And how basically the operating system schedules, like a short-term scheduler and a long-term scheduler. Again, you don't have to memorize a lot of the terms. That's why I'm trying to at least prevent, so that the questions are not like that. Try to of course study as much as you can, but on the other hand, just know that the more importance is not memorizing things, but actually understanding, so that you can solve those exercise type of questions. All right. Also the inter-process communication. So what was message passing? What was asynchronous or synchronous? What was like blocking or non-blocking? How did the send and receive message work? Again, not in terms of like, okay, send message was like had an argument of like P or Q. Not like that necessarily, but at least the difference between like a blocking or not unblocking. What was the difference? All right. So I'm not going to ask like what is the rendezvous, type of communication that the waiter, the sender should wait, or the receiver. That is kind of not very OSy. All right. So then we learned about concurrent programming, and what were the benefits of concurrent programming. What was the difference between the threads and processes? What data was specific to threads? What data was specific to process, and an overall of the threads. And then in what cases a thread pool could be used, and what was the benefit of doing this and not creating and terminating so many threads. And then the implementation and multi-threading models. This was something that I think some of the students did not do well on the homework or quiz? Homework. And just make sure you understand the threading model, the one-to-one or many-to-one. What you probably have worked with is the one-to-one, which is implemented, for example, in I think Windows and Linux, and that is when each thread is assigned to a kernel thread, and makes sense. But there were some issues with that, or some benefits to the other approaches. Just know them, and so that if something like that comes up, you can think about that. Then there were other issues that, like for example, what happens if a fork is called by a thread? Are all the threads copied or not? If a thread calls exec, then the whole process is getting replaced. So what happens to the threads? Do we have like many threads or no? These were just like, again, thinking. You don't have to memorize everything there, but and also the signal handling. We had like different type of how a multi-threaded process can handle the signals. We could like deliver signals to all of them, to some of them, to one of them. Some of them would be volunteering or so. Then we did not actually talk about process synchronization, but this is chapter 5. So in process synchronization, we learned what is a race condition, what is the issue of accessing a shared variable, for example, or modifying them, and then the problem of critical section. What is the critical section? What happens if multiple processes try to access their critical sections at the same time? How to avoid them? We learned about the 3 criteria for critical section solution, which the more important one was the mutual exclusion. We talked about it a lot. And then we learned about semaphores, monitors, and condition variables, and how they were implemented. Well, we didn't see the implementation, for example, for condition variables, but the idea was enough. But the implementation of semaphore, how we saw a couple of different implementations using like busy waiting, and then we talked about like, okay, which part of it should be atomic, what happens if, incrementing a variable or decrementing a variable is not atomic, what happens, how, that interleaving can mess up the whole use of semaphores. And then we had a few examples of the problems of synchronization. I hope you understood these all, and the codes. Make sure you understand their, sample codes, the bounded buffer, readers and writers, dining philosophers, and sleeping barber. Again, today hopefully we'll go over a couple of examples of those and see they can be just like slightly, tweaked, and then it becomes a new problem. So you have to understand what was the issue, how to solve it, how to approach it, so then you can, fix it, or at least, to be able to tell what's going on or what's wrong. All right. So before that, in CPU scheduling, we talked about scheduling criterias. What was like, throughput, waiting time, service time, turnaround time, response time. And then we learned the scheduling algorithms: first come, first serve, shortest job first, priority, round robin. Also, a couple of those, we learned what is preemption, how can we preempt, what happens during a preemption, and then what is the difference between those algorithms with preemptive or non-preemptive. Then we learned to draw Gantt charts of the schedulers, and given a set of processes with the burst time, some information, arrival time, and then be able to start drawing them and figuring it out, how to approach. Again, there are a couple of examples on the lectures, and I think in recitation, one example maybe. And then basically the performance measurement. So after the, making sure your Gantt chart is correct, then deriving all the response time, waiting time, turnaround time, maybe, average them if you want to compare them, whatever. So these are all the type of questions that you can expect from the CPU scheduling. Then we learned the estimation of the CPU burst time using the averaging window, the exponential. And again, that is something to understand and remember. So what was the alpha? How could it, how would it affect if the alpha was closer to 1 or 0? Which way we would pay more attention to the recent history, which way we were like, less reluctant to change our perspective of the process. So you don't have to do a lot of, math there, but knowing what was the alpha parameter at least is the key. Speaking of, by the way, math, you might end up doing some calculations in the exam. They are basically simple. They are at most the same thing that you've seen me doing on the blackboard. Adding a couple of numbers or dividing them by 2 maybe, or maybe even not division. But so if you would like to bring your calculator, simple calculator on Tuesday, it's okay, but not a calculator on a phone. We're not going to allow that, right? So I'm just, if you want it, again, you don't probably need it, but if you feel like, so that, you don't make a mistake or something, bring your calculator, it's fine. And then we also learned about the multi-level feedback scheduler. Yes?
Simple calculator and put a scientific one?
It's, I guess, fine. Like, I really don't know how to, check which of them, have a memory or something. But if it's like one of these TIs, and then you're spending, half an hour on it, or, good. It's just... The calculator's usage also is basically expected to be very short, right? Because you just want to do... Yes. What's that? Scientific. That was his question. So the scientific calculator. It's fine, I guess. But again, we would probably ask you not to, keep it, at all times there, just to make sure that, again, we're trying to, prevent as much as we can. We don't want to pinpoint anyone in specific, but things can happen, and we want to prevent that, right? At some point, actually, I may actually say, okay, I removed those questions, or I made the numbers simple, so you don't have to bring them out. All right, so the multi-level feedback queue scheduler, you have to, I think by this time, looking at the Pintos or questions also, you know what is it and how the different queues working, what are the criteria, you can have different, scheduler for different queues, and then what is the feedback part, how can you, age, what is, again, you're probably not going to be asked, not probably, you're not going to be asked, okay, what is the range of a nice value, right? It's just not very useful, right? But I may bring a couple of questions from Pintos code. Nothing that you have to go and read the code just for the exam. No, as long as you have seen the code for your project, you should know what is the function of sema down is, and at least know, okay, why we are doing this, why we are turning, for example, interrupt off here, whatever. So a piece of code might be given from the Pintos, just and ask what is this line. All right. So then, during the last couple of lectures, we have talked about deadlocks, characterizing them, the 4 necessary conditions for a deadlock, and then how to use a resource allocation graph to show if the possibility of a deadlock and resources to processes. And then we talked about the prevention, avoidance, detection, and recovery for deadlocks. And then we talked about the safe state and safe sequence. These are some of the things that you might actually expect in the exam. And the exercises during the past couple of lectures, you have seen how we draw that, charts, and then we work our way out, based on the available resources, how should we allocate or not. And the differences also in the detection algorithm and Banker's algorithm. So one of them was basically to detect when the deadlock has happened. If not, we don't care. We didn't care. The other one actually wanted to ensure that we stay in the safe state. So they had a very similar algorithm, but it was basically assuming that we allocate and then a check again, and then the possibility of a deadlock instead of a deadlock, and also the wait for graph, which was used in the detection one. All right. Any questions in just going over titles like that? If any of them was not clear or something, we can talk, and then even I will bring up those slides and then talk on the slide, in depth. Okay, so just let me know. Yes.
So I remember in homework when we have to draw every time thread 4.
Yes. Yes.
Can you go over that again?
Yes. We have. I have the same example in the slide. That same example actually is solved in the recitation number 2. Make sure you go over that. I might actually go over it on the board just to tell you how it works. But fork and exec is something that you probably can expect a question in the exam. All right. So now let's go over a few of the exercise questions. So some type of the questions are true and false, right? So let's go over them together. So in multi-programming, it is safe to have an arbitrary number of threads or processes reading a piece of data at once. Is it true or false? True. Why? Because it's reading, right? As long as you're reading, it doesn't matter that the consistency is not it holds. Kernel mode can directly access hardware devices. User mode cannot. Is it true or false? True. Deadlocks cannot arise without semaphores. Is it true or false? No, that's a little bit more quiet. False or true? Why? Raise your hand. Yep.
Semaphores don't prevent deadlocks, they just prevent race conditions.
Okay, so do you say this is true or false?
False.
False. So deadlocks can happen without semaphore? So you say true. False? Why? How?
Semaphores are just like a form of prevention. They don't guarantee that it won't happen.
Semaphores are not, they are preventing mutual exclusion, right?
There's a few other
Okay. Okay.
There's other ways that processes will wait on resources.
Okay, so that kind of complements that. There are other ways that this can happen. Semaphores is one way, yes? What's that? Well, circular wait is, but you're still waiting, right? If you're waiting on a semaphore, it is still caused by a semaphore, right? The wait is actually there. Circular wait is necessary, but you don't have to necessarily wait for a semaphore. For example, mutex locks can be implemented without semaphores, and mutex locks can cause deadlocks. So deadlocks they're still waiting, but on a different type of resource, not semaphores. Or they might be just waiting for I/O, right? So, this is false, and the reason is these are not the only things. So semaphores are destroyed by the operating system when your process exits. True or false? True? True? No. And that's the thing that you have to take care in your Printos code. Semaphores are different independent data structs, which are, allocated memory. The reason is because they're shared. So, they're by some processes, they're like, ups and downs. So, which process, when it exits the OS, should destroy it? The other processes might still need them, right? So the OS does not do that. A process that is blocked is not given any processor time by the scheduler until the condition that caused the blocking no longer applies. Is that true or false? Yeah? True? Yeah, that's the meaning of the blocking, right? That's what you try to implement instead of the busy waiting so that it does not, take the CPU time. Alright? So, these are, some type of questions might be like this, true or false. So, a system that meets the 4 deadlock conditions will always, sometimes, never result in deadlock. Which one? Which one? Sometimes. Why? Why sometimes? Yes. Yes, correct. So we have 4 conditions for a deadlock. They were not conditioned for guaranteeing deadlock. They were conditioned necessary for a deadlock, not necessarily, guaranteeing. Right? So the 4 conditions are necessary but not sufficient. They only shows chance of deadlock. So round robin scheduling always, sometimes, never results in more contact switches than first come first serve. Think about it for a moment. Round robin versus first come first serve. The number of times the switch contact switch happens. Is it always more? Is it sometimes more? Is it never more? Who says sometimes? Who says never? Who says always? No one says always? Why always? What's that? Exactly. So because of that chance of equal, it's not always. It's just like a bit of a, mathematical, So, if every job has an execution time less than the quantum, basically it turns into a first come first serve. So it's not, the number of switches is not more. If it was asked, is first come first serve ever less than, first come first serve more than round robin, that would be never. But this we can say always. Alright, so which of the following scheduling algorithms can lead to starvation? FIFO, SJF, priority, round robin. Yep. SJF and priority, we learned this first come first serve, and round robin, there is a queue and eventually you come, in the round robin you actually keep going and coming at the end of the queue to the head of the queue, so there's no starvation. But short job first and priority, there are always lower priority or longer jobs that should wait, and it's not like combo effect, they actually have to wait maybe forever. So when handling deadlocks, what approach uses the wait for graph? Prevention, avoidance, detection, or recovery? This we basically talked about last session. The wait for graph. Someone from this side. Okay, Taha, you also have answer. Detection, yeah. So last session we learned about detection, and for detecting a deadlock for a single type resource, you remember we were changing the resource allocation graph to wait for graph, and then we just search for a circular wait. If there was it, then it was a deadlock. Okay, so it was for detecting a deadlock. All right, so consider setup processes below. This one is for scheduling, right? So it's drawing a Gantt chart illustrating the execution of these processes using preemptive shortest job first. Remember, whenever you're dealing with scheduling, make sure are they preemptive or not. And so then it's asking for waiting time, turnaround time, and so all right. So we don't have a lot of time right now, so that I wait that you actually solve it. I wish we had, but I guess I'm gonna just go and draw it, and but make sure you're paying full attention, because this is, I think we've been over this. And who watched the video on the exercises of the when I solved the scheduling algorithms at the end of lecture number, what was it? 9, 8, 6? What? It was the long one. Who watched it on YouTube? Just raise your hand. It's fine if no one. Okay, a couple of people. Do it, because that gives you actually much more information than what I'm just going to do it now. If this is one example, one type of scheduling algorithm. There I have done all of them, so it's definitely worth spending the time if you want to learn this, right? So we have A, B, C, D, and E, and then we have arrival. We have 0, 4, 12, 16, and 20. And then priority is given. We don't actually care about priority in the shortest job first, so I'm not going to even write it down. And then the burst, what is it? Is it 20, 12, 16, 4, and 8. All right. So it's because it's preemptive, you have to also pay attention to the arrival times. Otherwise, you could have just started at the startup and finished. So starting at time 0, what do we have? We only have with the burst time of 20, right? So this gets scheduled till when? Till either 20 or next thing that happens. Next thing is at 4. So at 4, what happens is B comes with the burst time of 12. What is the state of A at this point? 16, right? It started with 20 burst, executed for 4 millisecond, whatever, and then now it's basically 16, and now B is arrived with 12. So because it's preemptive, now we have to actually turn to B instead. So A gets scheduled out and B gets scheduled. So then it goes on either for 12 or 12 more milliseconds, or at the time where D arrives, which is 8 milliseconds from here. So at this time, B has executed for 8 milliseconds. So what is the state of them? A has not changed, 16. B has reduced down to 4. And now, C has arrived. Sorry. This was misalignment. Okay. So, C has arrived with the burst time of 16. Okay? So, we should not schedule out B. It should just keep going because it's still the shortest one. So, for 4 more milliseconds it goes on. And then B, basically it doesn't finish here. And at this time, B finishes. We have A with 16. C with 16, and then what else has happened here? D arrives with 4. So because D is the shortest one, D gets scheduled, and then it runs for 4 more, where E arrives. So at this time, D finishes. A is still 16, C is 16, and E arrives with 8. Again, amongst these, E starts, because it's the shortest one, for 8 milliseconds. It runs from 20, sorry, I didn't write 20 here. I'm just going to write it here. So to 28. And then here we have A 16, C 16, and E is done. Between A and C here, again, is the, you have to make your decision sometimes where there's a tie, and you have to break it usually with FIFO. So A arrived first and then basically got scheduled out here, so it was already waiting to be scheduled from here, with the time of 16. C only arrived here with the time 16. So A has arrived or was ready sooner. So A gets scheduled here and runs for 16 milliseconds up to 44, and then only C is left here, gets scheduled all the way to 60. Okay? So, now what are the waiting times and the turnaround times? This is actually part of the lecture note, so you don't have to draw it the numbers exactly, but as long as you know how to derive it, that's fine. Okay? So, the Gantt chart, again, it's useful to have it a draft and then, mark it, whatever, and then do it one more time just clean so that you can double check the numbers, right? If you did it right. And then, the response time for A was 0 because it arrived right there. For B was 0 because it got preempted. It got, finished. D arrived, right here, and then it went. So the response time for D was 0. For E was also 0. And, for C was quite a bit long because C arrived here at 12 and then it waited so long, so that's the response time is 32. Now the wait time, you remember, wait time is the total wait time. So it's response time also the rest of the wait time that was waiting. So for example for A, even though it started right there, but it has been waiting from here all the way to here, so 24. For B, nothing. C, from here to here, the whole response time only. So this is a relatively simple example. D, again, 0, E, 0. Turnaround time from arrival to finish. So TA finished here and arrived here at 0, so that's like 44. TB finished here and arrived right here at 4, so that's 12. C finished here and arrived here at 12, so that's like 48. TD finished here, and then it arrived here, so that's like just 4. And TE is also here, just the service time, so they didn't actually wait. You remember there was also another way to calculate it. It was like service time or burst time added to the whole wait time. All right? So then, next question. Was it any question in this one? Okay? No? Okay. So, this is the question that was with the fork. So let's take a look. This is the same question, the same code, and even the same letters. But which again is in the recitation slide, so I'm just going to go over it again here, but not very, step at a time, a little bit faster, just to see. So just remember a few things to note when you're dealing with these questions. First of all, remember that to read the assumptions. If the PIDs are set to 0 beforehand, well, they're 0. That's the initialization that's been given to you. And whenever they're assigned to a fork, the parents get a non-zero, the child gets 0 for that, value. Don't get confused with the name of the PIDs. These are just the name of a variable. You have to just, they're just like X, Y, Z, whatever. It doesn't matter. Remember, when a process runs the execp successfully, there's nothing after that. It does not return from this function call. It does not go to the rest of the lines. If And then again, the assumption usually says that, okay, after that, doesn't print anything or it doesn't fork, so we don't care. Anything before I change it? Yes. Okay, go ahead. This one.
Yeah. So we keep subtracting the burst time. So if we like produce like if we schedule for like 4 like 16, does that replace the kind of like the priority like where like when we schedule it, or do we just consider the original one? Because I wasn't thinking about that first.
Oh no, we have to. Yeah, that's what we have done here, right? Definitely, you have to update the burst time. The burst time is basically what you care is the remaining burst time, right? So, especially in the case of a preemption, like the difference between the preemptive SJF and non-preemptive is that in the SJF non-preemptive, when you schedule a process, you don't even look at what has happened all the way till that process is done. And then by that time, you exactly do this. You see, okay, at this time, what do we have? Right? We have process A with this, B, C, and in this time, for example, C has arrived, so I'm going to write it down. Okay? So in the preemptive shortest job burst, you have to see at what happens in the arrival time. So, for example, when A got scheduled here, it did not run all the way to the 20th millisecond. Why? Because right here, B arrived, and then you have to, again, call the scheduler and make a decision. At this time, what do I have? A was started like 20, but at this time, the remaining is 16. Because it has executed for 4 milliseconds, right? And now B has arrived, which is 12. So what is the best decision to make based on the SJF algorithm? Shortest job first. Amongst these, the shortest one is B. So now I'm going to schedule B. Right? And then at this point, for example, again, B is not finished, but C has arrived. Because you are preemptive shortest job first, you have to make the decision and see if you should preempt B or not. So here you write it down again. A is still 16 because it has not executed from here. B has executed from here to here, which is 8 milliseconds, so it was 12, now it's 4. And then C has arrived with 16. So now I make a decision. What is the shortest one? B. So I just let that run. If C also was 4, this was a question another student asked. If at this point C is 4, C is not shorter than B, so you don't preempt B. In the case of a tie, in this case, because the new arrived process is not shorter than the current, so you don't actually go through a hassle of extra context switch. I think, again, in that example that I solved on this board and recorded, I think that was one of the examples. So you just let that run. In this case, again, we let that run. So you have to recalculate the burst time, the remaining burst time as you go on. Yep. All right. So next, going forward, the code, and actually maybe I want to leave this. So the answer is here, but I guess you don't know how to derive it, right? So let's go over this again, but I can't write the whole code. I hope you have the slides or on your laptop or phone or whatever. I'm going to look at this monitor here and then go over them on the board. But I have to be a little bit quick again because we have a couple of other examples that I want to make sure that we reach. Okay? So, when you have PID1 fork first, so you have the parent process here, initial one, and then each fork you actually fork, right? So when we run PID1 is equal to fork, PID1 in the parent process becomes a non-zero variable, and then we have a fork. Which side have I forked? I just want it to look like the other one. So the fork 1 creates another process here which has the PID1 0. Right? And we usually don't write down the rest of the PIDs if there's not enough space, right? And then exactly on the next line is PID is equal to fork. Which process is running that? This is important. And you have to make sure whenever you are drawing or creating a process, you have to make sure from which line they start running. So this was created after fork 1, after that PID is equal fork 1. So this starts right after that line. So this also runs the PID2 equals to fork. I wish there was a way that I would like turn on half of the projector. So fork 2 then goes towards the right side. Right? So fork 2, this runs as and because this is the parent process that forks, this creates a separate process with the existing variable. So this process is a copy of this process. So PID1 will be non-zero. Now, after fork 2, PID2 in this becomes 0, non-zero, and PID2 in this one becomes 0 because this is a child of this fork. Now, this process also runs the execution code after that line. So this also goes through the fork 2. So when this runs that line, this creates fork 2, another process which is a copy of this one. So the PID1 is 0. However, this is a child of another fork. So PID2 will be 0 in this one. PID2 will be non-zero in this one. Okay? So far so good. So then we have that, text box over there that said if PID1 is non-zero. I mean, at this point, all of them run this if. One thing you can do is, if it helps you out on a draft paper, you can just run one process at a time completely. So you can just run only this process and then see what happens, to its fate, and then, move on. Or you can start branching and, running all of them together. It doesn't matter. It's just you should feel comfortable with whatever. So, all of them at this point run, if PID1 is non-zero, then they fork. Else, they print B. So that means if PID1 is 0, they just print B and exec V. So PID1 is 0, meaning these, they print out B, and then just go on. There's nothing else to be done on these. Sometimes this helps, right? So then it says, okay, now if PID1 is not 0, fork 3. Now fork 3 is, to the side. So this fork gets a copy, exact values, PID1 non-zero, PID2 non-zero. This is a child of the fork, so PID3 is 0. Okay? Okay. Now, in this one, after this fork, PID3 again is non-zero. Okay? Now, the same thing is happening on this one, because this also goes to the if and then runs the fork. So the fork 3 runs on this, copies it with the exact values. PID1 is greater than 0. PID2 is 0. This is a child. PID3 is 0. PID3 on this one, however, is non-zero. Okay? And after this, PID3's fork, all of them run print A. No matter their child or parent, they print A. So this prints A, this prints A, this prints A, and this one. Then we come out of that if, the next if. If PID2 is 0 and PID3 is non-zero, exec V. And then print C. But there's no then. Exec V and done. If PID2 is 0 and PID3 is non-zero, exec V. That's it. None of them, the other one, don't care. Now, then the rest of them fork number 4. So this one runs fork 4, makes a copy. PID1, I'm just going to write P1, is not greater than 0. P2 is also non-zero. P3 is 0. And then P4 is also 0 for a child. However, for this one, P4 is going to be non-zero. Okay? because it's the parent of this fork, and then it gets a non-zero. Also, this one forks for number 4. Goes up. Fork number 4. PID 1, non-zero. PID 2, non-zero. PID 3, non-zero. PID 4 is 0. This one also gets PID 4, non-zero. Then this one forks. This is down. Yes. I don't know why it's like PID 1, non-zero, PID 2, 0, PID 3, 0, 4 again for the child is 0, PID 4 for this one is going to be non-zero. So after this fork, all of them keep running, and it says like print D. So all of them who went through the fork 4 print D. So this is A and D. This again is also after this A and D. This one only D. This one again had, okay, and then it asks if PID 3 is non-zero, then we should do something. Okay, so PID 3 non-zero, none of this, this and this, and not those. So okay, what do we do with these two? Print E, fork, and exec V. That's a little bit harsh. So E, then fork 5, so just remember, I'm just going to write down 0, 0, 0, 0, 0, all of them. This one, because of the fork 5, the PID 5 is going to be 0. I'm sorry that the notations is not very clear, but I'm just narrating. So, and it's in the lecture note, so it doesn't, I think, matter. This one again gets its PID 5 greater than the 0 because it's a parent. This one gets everything from here greater than 0, greater than 0, greater than 0, and greater than 0. Sorry about this one. These are not all zeros. These are greater than zeros. This is equal to 0. This is equal to 0. My bad. Alright? And so the 5, however, here is going to be equal to 0. Because it's a child of 4, 5. But anyways, it didn't matter because after this, they all run the exec V after fork. So all of them just like go. Alright? After fork 5. So there is only a piece of code that remains that says like print F. Which process remains here? Those two and these two. So this runs, and then this runs, and then all of them call exec V again. Yes, did I make a mistake? Yes.
So child of fork 5 happens is created after the if statement. So I wonder that if a child of fork 5 can satisfy the if statement, because the if statement.
Which if statement? The fork 5 is.
If PID 3 isn't 0.
Well, if a process is PID 3 is non-zero, then you run the fork, and then that fork creates a child process very similar to this. So here, in this process, the PID was not 0. PID 3 is non-zero, right? So then it forks 5 and creates a child. So when it creates a child, every PID that existed so far, 1, 2, 3, 4, are copied. This is like the fork 5, and the value of fork 5 is going to be stored in PID 5, and then that PID 5 for the child is going to be 0, for the parent it's going to be non-zero, and then both of them continue exactly this next line, which is, exec VP. Okay, so let's talk about it later maybe. And then after this, all of them run the exec VP, and there is no PID 6 fork, so all of them basically are done. And then nothing runs the 6th fork. Alright? So, this is how to solve this type of question. Next. So, semaphore binary, the X and Y are running this, wait on S, wait on T, signal T, and then signal S, and Z is waiting T, waiting on S, and then signaling S and T. Is it safe to run X and Y together, or is it safer to run X and Z? So if X is running this, and Z is running this, what happens if X axis gets S, and then Z gets T, and then wait for each other? That's a deadlock, so it's not safe. But if X and Y run the same thing, and then you run them together, well, the one that accesses or gets the S, then the other one is like waiting for S anyways. So then the T is still available to whoever got the S. So there's no deadlock. That's just like the ordering. So here is atomicity, basically. So when we have like a wait and signal, what can go wrong if two threads basically run and there's no atomicity? So remember, what is the shared variable here? S. If S is decremented here and one is incremented here, if you actually think about it and go through it, it actually does not make it wrong. The problem is caused when one should not enter here, but actually enters here, right? So here does not need any guarding, but here is the guard. So if this guard and this decrementation actually are not atomic and not like, they don't run with the interrupt off. So what happens is that like one thread can run this while S is, less or equal 0 loop. Let's say S is 1. So this while loop does not happen. So the semaphore is available, it's 1. One thread actually goes beyond this line, but right before decrementing it to 0, another thread also runs, downs on a sema, goes into this loop, passes this while because it seems it's available, and then two threads are actually in this critical section at the same time, and then both think that the sema is available, which is not. One of them should only take them, the other one should not. Okay, so this is one scenario that just thinking of the order of the execution can change the result and show what's happened. Okay, and that's why the semaphores should run with the interrupts off, even for a short time. So, does this code guarantee mutual exclusion of two threads from their critical section? This is important. I'm going to go over it, but the explanation is in the lecture notes. So you see, if two threads of their critical section is here, the mutual exclusion means that not both of them enter their critical section, right? So let's say this thread has entered critical section. By entering the critical section, it has definitely, the first thing that actually it does is that setting the lamp 1 to true. If lamp 1 is set to true, then this thread cannot pass by this while loop, because it's waiting on the lamp 1, and the lamp 1 is not modified in here. So if this thread is here, lamp 1 is true, and then when this one enters here in the while loop, it just like loops whatever here. It doesn't matter. We don't care. It does not go into its critical section. So it actually satisfies mutual exclusion. Also, you have to think about the corner cases. So what happens if this lamp true runs, but this lamp true also runs? So both of the lamps are now true. So even this one doesn't get to actually go to the critical section at this point. But because this goes into the loop, this one also goes into this loop. But because the value of a book has either 0 or 1, one of them will enter this if and then set its own lamp to false, and then that makes the other one exit the loop, go to its critical section, and then this one is still in the while loop, and it doesn't enter its critical section. So the code does not matter very much in this case. You just have to think, does it guarantee mutual exclusion? Is it possible that two of them enter their critical section? No, there's no path of execution that allows two of them enter their critical section. But I can't give you the time to think, but the code actually is not correct in the sense that it does not guarantee progress. There's things going wrong in it that does not guarantee progress. So just remember, progress and mutual exclusion is different. If there's something wrong with this code, they don't both run, that doesn't have anything to do with the mutual exclusion. Okay? So I think by fixing this book to 1 and this to 0, it becomes fixed. But you can go over it and see. All right. So the next type of or next questions is regarding alpha. Remember, for when alpha was the how likely we are to change our perspective of a process based on recent behavior, right? So if we had a prediction, it doesn't matter when alpha is 1. Our prediction doesn't matter. We want to quickly change based on the most recent behavior. So whatever the last burst time, actual burst time of the process was, we're going to take that as our next prediction, right? We're going to forget all the history. Alpha 0, we don't want to change our perspective of the process. So if we had a prediction, we don't care if the process changed its behavior or the burst time, did not match or whatever. We're just going to keep the same prediction. So this is just the extremes. The alpha is like a range, and it's likely. So this was the formula. Again, alpha is multiplied by the Tn. If you just multiply 1 and this becomes 0 clearly. Next prediction is the previous burst time, no previous history. If alpha is 0, this is going to be all 0, and then only the prediction just keeps continuing. So no recent history matter. You don't have to memorize the formula again because we're not going to calculate. But the fact that what is alpha is important. Actually, yes, you don't have to expand the formula as we did in the lecture, but just like this small one, yeah.
So in both cases, the S is Tn.
No, this is Tn, this is tau n, or like capital T. This is the prediction, this is the actual burst. Okay? So we talked about this one last session or last week. About the resource allocation graph, we draw and then show that there is a chance of a deadlock in this situation because the way that the order of the gets are running, right? So if both of them, if all of these processes run the first 2 lines, this gets A and B, this gets D and E, this gets C and F, then all of the resources are taken, and then all the processes are waiting on the third get. And then it's a deadlock. Again, this one gets A and B, this one C and F, this one D and E, there's no problem with that. But then this one is waiting for B, this one is waiting for D, this one is waiting for C. So it's a deadlock. How we can fix it? That was an exercise. To reorder this. Remember that? In the dining philosopher problem? One solution for a deadlock. No one? Come on. You don't remember? All right. So one thing, if you remember, the dining philosopher was that everyone wanted to grab their right-hand chopstick first, and that was a problem because everyone that. So then we reordered the chopsticks, basically made them numbered, and then made a rule. If you want to get 2 chopsticks, you have to get the chopstick with the lower number first. Here also we can basically, they're waiting for multiple resources, we can ask them or basically expect them to request them in an alphabetical order. So if we change it to ABC, BDE, and CDE, what happens is that if this one passes B, if this one gets B, then no one else can get B and pass something beyond B, because B is already taken by this. If this one gets B, that means it won't go back to something before B. So there will be a order of execution. We can't guarantee this, right? So if this one gets C, for example, we can make sure that C, this cannot get C. Now, if D is taken, that means this has B and D, and this waits on D. So this doesn't go to this. And then this, if this has D and E is available, this gets it, finishes, releases B and D, and then the other one can go on. So once you have an order of your resources, such as like numerical or alphabetical, and then you make sure all the processes, if they are getting multiple resources, they get them in the order. A before B before C. B before D and before A. Not vice versa. This prevents deadlock. Okay? Yes? What's that? Yes, that's the assumption that when they actually enter their critical section, they finish, they release. That's always the assumption. All right. So the next question, I think you have seen with the time quantum. So I guess I have to skip this. But if you have a question posted on Piazza, I actually meant to solve most of these, but I guess I was too optimistic. So another question that has added to this is under what condition will the wasted fraction of CPU time be 50%? So you have to calculate this we have a context switch, and then we have a quantum, and then this total is S plus Q or S plus T, what happens. So when T is less than Q, meaning we don't actually get to do the quantum. So we run for T, and then we have a context switch. And then next process, we have a T, and then we have a context switch. So for each process, we are running T, and then we are wasting S. So that's for every T plus S, we are wasting S. So that gives us that. Now if T is very long, so one process, let's think one process is running, it uses one quantum Q and then wastes S for a context switch. Again, another Q, and then again a context switch overhead. So every Q plus S, we are wasting S. So that's why when you divide that, you get this. There's also another way to calculate it, and that's it. Basically dividing T by Q. Say, okay, how many quantums we want for this process? T divided by Q, because we're running by Q, so we need these many times. Each time we are wasting an overhead of S, so total waste is this much. Total runtime is this much. So again, when you divide that, this number actually goes by this number, they cancel out, and then you get the same thing. It's just like a more complex version of calculating the same thing. As Q goes to 0, you're just you don't actually have runtime. You quickly are context switching, back and forth. You're just not doing any useful work, and the waste goes to 100%. And the answer to the other question is basically just looking at these two fractions. If you have S equal to T, then this becomes 50%. Or in this case, if S is exactly as Q, then this becomes 50%. This is just like a, special condition, right? So then the sleeping barber problem, we cannot solve this right now. It actually requires you to think through, but the understanding what the lecture note gives you how to solve this. This is another type of question that you might actually see. There is a piece of code that you have to write something in it, right? In this case, there are the semaphores. You have to know which semaphore weight or signal put where so that it makes sense, right? The other problem, this is a new problem, similar to the dining philosopher, slightly different. There are 3 people, each has one resource, and they're waiting for another resource. And then there is a distributor or an agent which provides paper, tobacco, and matches to puts on the table. One person has the matches and it's expecting for paper and tobacco. One person has the tobacco and then waiting for paper and match. The other one has the match and waiting for paper and tobacco, if I said it right. So how the agent, in what order, should basically provide these semaphores, and then they wait on them and signal them how these is working. So you have to look at this and think through. But make sure, just note that the code is not actually perfect. This code is not flawless. It's fine that you find it out. Just 1 second so I go over this. So remember to practice quiz and homework questions and solutions. Make sure you understand all of those. With regards to your PA1 implementation, don't set it aside for your exam. You have to work on it. By this time, you have to be done with alarm clock, all of you. Most of you should be done by implementing the priority scheduler itself. At least half of you should be done with priority sema. Some of these issues, you might have a struggle. That's fine. You should debug. But if you're not implemented them, you're kind of behind. I'm just giving you heads up for next week because it's going to be hectic. And basically, this is the time that you should think about priority donation. If you want to go with nested donation, Next week, next, final few days, I would say just, for MLFQS. That's a whole other story. All right?